Today we're looking at graphing exponential functions. Our learning targets today are that we will be able to graph an exponential function and that we will be able to determine if an exponential function represents exponential growth or exponential decay. So we'll start off with this equation, which is a review, y equals 3x. And this represents a linear function. Good. So when we have y equals 3x, we can complete a table of values to give us some points. When x is 0, y is 0. When x is 1, y is 3. 3 times 1. When x is 2, y is 6. Good. When x is 3, y is 9. And when x is 4, y is 12. Okay, so we can see that as x increases by 1, y increases by 3. Okay, so we have a linear relationship. As x increases by a constant amount, y increases by a constant amount. Slope would be rise over run, or plus 3 over plus 1. Okay, we would have a slope of 3, I heard someone say. All right, but now let's look at a new type of equation or function when we have y equals 3 to the x power. Now this is different than any of the other type of function that we've looked at before. Now our variable is in the exponent. And whenever we have a variable in the exponent, that's going to give us an exponential function. Okay, so there's our variable x. It is in the exponent. Okay, so if we want to fill in some additional values, I actually want to add a few more here. So just cross that off, or you can write over it. I'm writing mine out. I'm going to add a few more values to our table here. I got a -1, -2, and -3, and that'll be good enough. Okay, so when I have x equal to 0, I will have y equals 3 to the 0 power. And we know that anything to the 0 power equals what, boys and girls? 1. Nice job. 1. When x equals 1, we will have y equals 3 to the 1 power, and that will equal what, boys and girls? 3. Nice. If x is 2, we will have y equals 3 squared, which will equal 9. Thank you. If x is 3, we will have y equals 3 to the 3rd. 3 times 3 times 3 is 27. And then another factor, 3 to the 4th power will be 27 times 3, which will give us 81. Okay, nice job. And then remember what we talked about with the reciprocal relationship when we're dealing with just a base to a power. Okay, we know that if we have x equals -1, we will have y equals 3 to the -1 power. Well, 3 to the -1 power is the same as 1 over 3 to the 1st power, or 1/3. Okay. If x is -2, we have y equals 3 to the -2 power. Okay, y equals 3 to the -2 power. And to make that exponent positive, we need to move it to the denominator. So we will have 1 over 3 to the +2 power, or 1/9. And then do you see this reciprocal relationship here? 3 and 1/3. 9 and 1/9. And then 3 to the -3rd power will be 1 over 3 cubed, which will give us 1 over 27. Good, I heard a couple whispers. Good. All right, so, and then we ran out of room to do the -4, but what would, if x is -4, what would y equal?
1 over 81.
1 over 81. Let me ask you a question. You can talk about this with your shoulder partner. So as x gets smaller and smaller and smaller, what's happening to y? As x gets smaller and smaller and smaller, what is happening to y? Okay, y is getting what, boys and girls?
Smaller.
Smaller and smaller and smaller, because each time we're dividing it by what?
3.
We're dividing it by 3. Okay, and then let me ask you another question that I want you to talk about with your shoulder partner. Will y ever become negative? Talk with your shoulder partner about that. Will the y ever become negative? I divided by 3, divided by 3, divided by 3. Each time I divided by 3. Okay, good. I heard Nico say it's just going to keep on getting smaller and smaller and smaller. It won't become negative because each time I'm just doing a positive divided by 3, a positive number divided by 3, a positive number divided by 3. So it's always going to be getting smaller and smaller and smaller, but it'll never be completely gone. Okay? So this is a limit. It will approach 0, but it will never equal 0 or become negative. If we take a look at this type of relationship here, what do we notice about x? As I increase x by 1, what's happening to y? Talk with your shoulder partner.
So it's like
Okay, so as x is increasing by 1, what's happening to the y values, boys and girls? Good, yes, it is being multiplied by 3. Okay? And that should make sense to you as we just spent the last 2 weeks learning about powers, because 3 is the base of our power. So we're looking at powers of 3. So each time we're multiplying by some power of 3. Okay, so what do we notice about the two tables? The table on the left is linear. Okay, meaning as x increases by a constant amount, y increases by a constant amount. Okay, the table on the right is exponential. As x increases by a constant amount, y increases by a constant factor. Okay, and then let's just talk about exponential functions. Exponential functions are functions whose values are constants raised to a variable power. Okay, and the parent function is y equals a times b to the x, where b is the base, and a is the initial amount or the starting amount. Okay, so exponential functions are functions whose values are constants, or it can be just one constant, raised to a variable power. Okay, and then that base parent function is y equals a times b to the x power. B is the base. Okay, A is the initial or starting amount. Okay, and we're using A for the starting amount in this parent function, but a lot of formulas, especially it seems to be common in finance formulas, we'll see the letter I, the lowercase letter I, used as the initial amount. So if you think of the word initial, you probably think of the initials of your name, the first letter of your first name, the first letter of your last name. So initial is the starting amount. Okay, if we're talking about our initials, we're talking about the starting letters of our names. So in this formula, it's A for, it's the starting amount. But in some of the other formulas that we will look at in this unit, you'll see the letter I used for the initial amount. Okay, so then there are two types of exponential functions, exponential growth functions and exponential decay functions. Growth functions increase from left to right. And this happens when because the base is greater than 1. Okay, when the base is greater than 1, the amount that's being raised to a power is going to end up with a larger y value each time. Exponential decay functions decrease from left to right. Okay, and here our base is between 0 and 1. Okay, and then if we look at the exponential curves, this is what the parent function okay. Here, what's our starting amount when x is 0, y is 1? So this is the graph of y equals b to the x, 1 to the x power. Well, b to the x power. Okay, and then decay functions, you can see our base is going to be between 0 and 1. Okay, you can see, actually let's erase this. This is, so in our exponential decay functions, you can see that exponential decay curve, and here you can see it approaches 0, but it never will reach 0 or cross over into the negative area. Okay. So this is exponential growth, exponential decay curves. All right, so here's our formula, y equals a times b to the x, and we're asked to graph the following exponential functions following all the steps needed. So number 1, we have y equals 2 to the x power. So we are asked to start off by making a table. Let's do -2, -1, 0, 1, 2, and let's just add in 3 so we can see that curve a little bit better. Okay, so here we see our 2 is what's being raised to the variable power. So we have 2 to the x power. And then the first question is, what is the a value? Okay, well, 2 is what's being raised to the power, so that's representing the b. So what must the a value be? What's that coefficient in the front? What does it have to be?
Y.
No, here's the y right here. Y equals a times b to the x. So what's missing here? What does this have to be? Well, no, because if I had 0, I'd have y equals 0 times 2 to the x, and 0 times anything would be 0. So it would just be y equals 0. So what does it have to be? 1. Okay, if it's not written, it's just 1, and it's been simplified in y equals 2 to the x power. So here, our a value is 1, which means our starting amount is 1. Okay, and what's the b value? That's the base. That's what's getting raised to an exponential power. So b equals 2. Okay, excellent. So let's go ahead and graph these. Or, excuse me, fill out our table. If x is 0, y equals 2 to the 0 power. What will that be?
1.
Nice. Okay. Anything to the 0 power is 1. Now, what if x is 1? Y equals 2 to the first power. What does that equal, boys and girls? 2. All right. And let's look at -1. Y equals 2 to the -1.
1/2.
Good. Nice job, boys and girls. 1/2. So 2 to the -1 power, if I want to have a positive exponent, which is simplified, I need to move this to the denominator. So it'll be 1 over 2 to the first power, or 1/2. And we see this reciprocal relationship. Okay, that reciprocal relationship stands out because we didn't have a leading coefficient. Okay, we won't always have this perfect reciprocal relationship if the coefficient is something else, like down here. Well, these are actually very basic examples, but you won't always have this reciprocal relationship. It's just the reciprocal here, and then that gets multiplied by a. All right, what about if x is positive 2? I will have y equals 2 to the second power. What will that be? 4. And then if x is -2, I have y equals 2 to the -2nd power. What will that equal?
1/4.
The reciprocal. Good. 1/4. Okay, and if x is 3, y equals 2 to the third power, which is 2 times 2 times 2. What is that?
8.
8. Okay, and we see as x is increasing by 1, what's happening to our y value?
Multiplying by 2.
Good. Times 2. Why is it being multiplied by 2? Because 2 is the base. Okay, we're looking at powers of 2. All right, and then we are asked to draw, to plot the points and draw a smooth curve through the points to graph the exponential function. So let's go ahead and graph. -2, 1/4. -1, 1/2. 0, 1, 1, 2, 2, 4, and 3, 8. Okay, so we have these points. We know we're approaching 0 on the left, but we'll never actually touch it. Do your best to smooth out that curve. Mine's a little straight there. Okay, and we see it start to grow gradually, and then it takes off. Exponential growth. Okay. All right, let's look at number 3. Yeah, 2, sorry. Y equals 1/2 to the x power. Okay, so here's our base that's getting raised to a power of x. So what's our base b? 1/2. And what's the a value here as well? It's also 1. Okay, so our a value, our starting amount, is just 1. Okay, let's do -2, -1, 0, 1, 2. If x is 0, I have 1/2 to the 0 power, which equals 1. Good. If x is 1, I have 1/2 to the 1 power, which equals 1/2. If x is 2, I have y equals 1/2 to the second power, which means 1/2 times 1/2, right, boys and girls? If x equals 2, I have y equals 1/2. This is our exponent here. As you see that x, it's very small, but it's there. 1/2 to the second power, which means 1/2 times 1/2. What will this give us? What's half times half? 1/4, okay? And then if x is -1, I will have y equals 1/2 to the -1 power. Okay, so I can take the reciprocal of that to get y, to make my exponent positive, to get y equals 2. Okay, and if x is -2, 1/2 to the -2 power. If I want to get positive 2 power, I take the reciprocal of the 1/2, so it's 2 squared, which will give me 4. All right, so then I can plot those 5 points. -2, 4. -1, 2. 0, 1. 1, 1/2. 2, 1/4. Okay. Smooth out that graph. This is an exponential decay. Okay, what happened to the x values? The x values, what, boys and girls?
Increased by 1.
Okay, and as the x values increase by 1, my y values decrease by a factor of what? Divide by 2, right? So that means that they decrease by a factor of 2. Divide by 2 each time, okay? Which is the same as times 1/2. Okay, so compare and contrast the two tables and graphs. What do you notice? Number 1 is a growth function. And I've noticed on number 1 that as x increases by 1, y increases by a factor of 2. Then I'm also noticing number 2 is a decay function. As x increases by 1, y decreased by a factor of 2. So number 1 is a growth function. As x increased by 1, y increased by a factor of 2. And number 2 is a decay function. As x increased by a constant amount, y decreased by a constant factor. Well, we'll stick with the numbers since we did numbers here. So as x increased by 1, y decreased by a factor of 2. Bless you. Okay, so now we're going to get into slightly more complicated problems. We're not just going to start with 1, we're going to have different starting amounts. Okay, so in number 3, what's our starting amount? 3. And what's our base? Good, because the 4 is what's being raised to a power, so our base is 4. B equals 4. Let's do -2, -1, 0, 1, and 2. Okay, if x is 0, Now these you won't see this same nice reciprocal relationship because once we get that reciprocal, which will happen here, we're going to multiply by 3. So that's going to change it. So we're not going to see the reciprocals in the table. They'll just be happening in the formula, and then we'll be multiplying that by 3. Okay. So if x is 0, we'll have y equals 3 times 4 to the 0 power. 4 to the 0 power equals 1, and then 1 times 3 equals 3. If x is 1, okay, we will have y equals 3 times 4 to the 1 power. 4 to the first power is 4. 4 times 3 is 12. If x is 2, we will have 4 squared. 4 squared is 16. 16 times 3 is 48. Okay, then if x is -1, we have 4 to the -1 power. What is that? 1/4, and 1/4 times 3, 3/4. If x is -2, 4 to the -2nd power is the same as 1 over 4 to the +2nd power, which is 1 over 16. And then 1/16 times 3 is, nice job, 3/16. Oops. Okay, so let's plot these 5 points. -2, 3/16, -1, 3/4, 0, 3, 1, 12. I think I'm going to come by 2's here. Oops, and I think I'm going to accidentally turn off the document camera. Okay, so I'm just going to come by 2's here so I can fit a couple more points on my graph. All right, so let's try that again. Sorry about that. And 112. I'm only counting by 2's on my y-axis. Okay, and that'll at least lets me fit 1 point here on the right-hand side of the y-axis. And you can see it just takes off. It just skyrockets. Exponential growth there. Okay, and we'll approach 0 but never reach 0. And then let's talk about the domain and range. Remember, domain is the set of all of the inputs, okay? The x values. The range is the set of all of the outputs, the y values. Will my domain go to -infinity? Yes, it can. Okay, it can just keep going left. It'll get closer and closer and closer to 0, but never actually touch it or to equal it. And then what about positive value? Will my x values go to positive infinity?
Yes.
Yes. So my domain is -infinity to positive infinity. And then range. Does this go up infinitely high?
Yes.
It does. Does it go down infinitely low? No. It approaches but never touches 0. So my range, it goes all the way down to, but not including 0. How do I say down to 0 but not including 0? What's my notation here? Parenthesis or bracket? Parenthesis. Open parenthesis. Okay, so we're not touching the 0. Okay, it cannot equal 0. It'll approach 0, but it cannot equal 0. So it gets a parenthesis. Okay, what if I wanted to include 0? I don't, but if I did want to include it, I would put a bracket. Do you remember at the beginning of the year I told you one way I remembered this would just kind of visualize a giant equal sign within the bracket? That means it can equal the 0. Can we equal 0 here? No, because it just keeps getting smaller and smaller and smaller and smaller and smaller. It'll never equal 0. It'll just get infinitely closer to it. Okay, so the 0 is not included, so it gets a parenthesis. And then does it go up infinitely high?
Yes.
Yeah, it can keep going right forever. We go off this chart very quickly, but it can keep going right forever. So to positive infinity. Okay, and then number 4, we have y equals 5 to the 5 times 0.2 to the x power. I just like working with fractions better because I can do those in my head quickly, more quickly than I can do. We're going to stay, we'll take our break a little bit late. So more quickly than I can work with decimals in my head. So we're going to, what is 2/10 as a simplified fraction, boys and girls? 1/5. So I'm just going to think of this as y equals 5 times 1/5 to the, I almost wrote a t there, sorry, to the x power. Okay, and remember we're going to take our break a little bit late today, so let's stay put. Y equals 5 times 1/5 to the x power. What's our a value? What's our starting amount? 5. Good job. 5. What's the b value or the base?
1/5.
Right, that's getting raised to the x power. So 1/5, or actually technically in this problem it was 0.2. So 2/10. And it's your preference if you want to work with the decimals. I would just rather work with the fractions, but it's up to you. So I'll just do, we have 5 spaces. Let's do -2 through +2, counting by ones, -2, -1, 0, 1, 2. I like starting at 0 because anything to the 0 power is 1. Okay, and then 1/5 to the 0 power is 1. 1 times 5 is 5. Okay, what if x is 1? I have 1/5 to the first power, which is 1/5. 1/5 of 5. 1/5 times 5 is 1. If x is 2, 1/5 squared, that means 1/5 times itself. 1/5 times 1/5 is 1/25. 1/25 times 5 is 5/25. 5/25 can be simplified to 1/5. 1/5 there. Okay, if x is -1, I have 1/5 to the -1 power, which I can take the reciprocal and have 5 to the first power. So then 5 times 5 would give me 25. Okay, and remember we're not going to see that reciprocal relationship in our table because we are multiplying by 5 at the end. If x is -2, I'll have 1/5 to the -2 power. I want to make that power positive so I can take the reciprocal inside. I would have 5 squared, which is 25. And then 25 times 5 will give me 125, which is going to be way off my chart. Okay, so I'm going to count by 5 so I can at least get a couple points here. Positive. Okay, so let's do -2, 125. That's going to be off our chart. I'm going to count by 5s on the y-axis. On the x-axis, I can just count by 1s. Okay, so then I have -1, 25. So left 1 up 25. 5, 10, 15, 20, 25. 0, 5, and remember we're counting by y's on the, or counting by 5s on the y-axis. So 0, 5, 1, 1. So right 1, and then up 1 would be about there because remember we count by 5s. 2, 1/5. It's going to be very, very, very close to that x-axis. Okay, smooth out that curve as best you can. And what do we have here? Exponential decay. Okay, domain. How far left can we go? Negative infinity. How far right can we go? Good. Positive infinity. Nice job. Range. How low down can we go? How below?
Negative.
So I can have a spot down here?
Wait.
0. I'm going to approach this because I'm going to keep dividing by what, boys and girls? Keep dividing by 5, right? A factor of 1/5 here. Divide by 5, divide by 5, right? And so it's going to get smaller and smaller and smaller as x gets bigger and bigger and bigger. Y gets smaller and smaller and smaller because each time I'm dividing by 5. But I'll never get to 0, right? It's always a positive number divided by a positive number. It's never going to be 0. I'll never have 0 divided by 5. So I'll always have something, no matter how minutely small it gets. Okay? But I'll never get to 0. So we're going to go down to 0. That's the smallest. Up to infinity. That's the highest. And we always write smallest to largest. Oops, that's infinity. Smallest to largest. Negative infinity to infinity for the domain. 0 to infinity for the range. Today we learned how to graph exponential growth and decay functions. We learned that in exponential functions, the base is greater than 1, and that in exponential decay function, the base is between 0 and 1. Bless you. Okay, and then please rank your confidence level on a scale of 1 to 5 and explain why you have that level of confidence. Nice work, boys and girls.